today.
Yes. Hi, everyone. My name is Vladislav Zavialov. I work at Oracle. We do software development in Haskell or Camel, infrastructure in Nix, and my role at the company is to work on our favorite compiler, GHC, of course. And today I'll be talking about a Haskell extension that we implemented called RequiredTypeArguments. You can read more about it in the proposal 281. Contains all the technical details, and in the corresponding user's guide section, very underrated, the GC user's guide. And we will start with a motivating example of a type-safe printf. So it is already possible to write a type-safe printf in Haskell without dependent types, using combinators. And this is what the formatting package offers. You can see that we have those directives like text and int, and also string literals for the parts in between. And then, depending on what combinators you use, combined with this %sign, the resulting type of the printer will change. It will gain additional function parameters. So this is already something that exists, but it's not quite what we want, because we want to be using the classic formatting string syntax with the directives right inside the string. And now what we have here is that the value of this argument, the value of this formatting string, will determine the type of the entire formatter. Depending on the number of % characters, depending on the number of directives inside the string, we will have a different number of arguments in our printf, which does look like it calls for dependent types. So how could we do that? What type could we give to printf? This is the question. Could it be a function from text or from a string, a normal term-level function? Well, the answer is no, because if we use a normal function, then the variable, here it's s, is bound only in the equations. Only at the term level we get the variable. At the type level, the rest of the type has no way of mentioning the text value that we bound, which means that we cannot inspect the number of directives in the text value. We cannot determine the rest of the type based on the number of directives. What we have to do is use a type level string, so we bind it using a for all, and for all is a dependent quantifier, because it introduces a type level variable, a type variable, here it's s of kind symbol, which then can be mentioned in the rest of the type, which means the rest of the type will depend on the instantiation of the type variable. And this is the general approach that we're going to take to solve this problem. We will start with a string which will have to be a type level string. Then we will use type families to parse it. So at the type level, we run a parser using unconst symbol and const symbol type families, which we also added to the compiler. And then we get a type level data structure. Here it's a list of formatting parts. So we get %s or %d for the directives, and then literals for the characters in between. And then we will move from the type level data structure to a term using the formatting package with the combinators that we've seen before. So it's going to look like we have a formatting string, but it's going to be translated during compilation into a formatting term that is possible already today with today's Haskell. And this is the API, the overview of the API for the users of such a library. We have a data structure formatting part with the 3 parts that we can encode. Obviously, in a real-world example, there would be more formatters here. Then we have a type family. Parse format goes from a type-level string to a list of those parts. Then we have a constraint. The evidence for this constraint will be the formatting term. And then we have the formatting function, which is going to expand into all of the arguments for the formatter. And this is the answer to our question on the first slide. What type could we give to this function? It is for all, s of kind symbol, then the constraint, and then a type family that will expand into all the parameters. But I've used amp here in the name. Why? Because this type variable s only occurs as an argument to non-injective type families, which means there is no way GC could possibly infer it. It must be specified at use sites every time, otherwise GC will just get confused. What formatting string do you actually mean if you don't specify it? And can you not specify it? Yes, you can, because the for alls are by default invisible. Typically, when you call a polymorphic function, you don't instantiate it visibly. GC does it for you, but here it cannot, so we get an ambiguous type variable. And this is what we've got to solve. We need to solve two problems here. In the design of any polymorphic function, we're dealing with two issues. How do we bring the type variable into scope in the equations at the definition site? And then how do we instantiate it at use sites? And there are 5 solutions here, depending on what extensions we are willing to use. 2 of them are new. Those are the things that we added to GHC. And now let's take a look at each of them. Solutions 1 and 2 are the classic ones. We add a proxy parameter. So if somebody has trouble understanding the code here, please stop me, because I hope those examples are accessible. So we have an implementation of printf using proxy. It binds the type level string as here, and then it can be used in the body and in the rest of the type signature, so it's accessible. It is in scope in both parts of the definition. And then at use site, we have 2 ways to supply it, to instantiate it. We can use an explicit type annotation for the proxy argument, or we can use a type application with the extension. Problem with this is the syntactic overhead. Those are just things I don't want to write. You can see there are a lot of characters. Imagine you had several parameters like that. You would have a lot of overhead at each use site. The second issue is that GC does not guarantee that it will erase the proxies. It can be a dummy value passed at runtime, even with optimizations, especially if you put a new type over it. So what we do, alternatively, if we use the allow ambiguous types extension, is that we just don't have the proxy. We just write in the documentation for our function that the user must use type applications, please, please, please. Otherwise, they get poor error messages. Well, we warned them. Doesn't work in high order scenarios. I will not show them to you, but in tricky cases, it's not sufficient. So sometimes proxy is still needed. And also, we still have this @ sign. I don't like it. But since it is quite useful to work with invisible type variables, we did add type abstractions, which allows you to bind them in the equations with the @ sign that at least addresses the higher order scenarios. Error messages are still in question. And finally, the solution that I'm presenting in this talk is RequiredTypeArguments, which means that we will have type arguments which are bound and supplied syntactically and scope-wise in the exact same way that we deal with term arguments. It's going to look like a term. It's not going to talk like a term. It's going to be a type-level variable. So this is the API that we actually want, the better API for printf. The for all will be with an arrow, not with the dot, meaning that the type-level string, it's going to be a type-level string, it will be supplied in the same way that you would supply a term-level string. It's going to look like a term, but it's going to be type-level. And now we are moving on to other small examples, because you can fake looking like a dependently typed language with this. So here is Idris 2. It has the function which acts like a type annotation. You supply a type, then you supply a term of that type. It is basically a type annotation. Here is a session. Idris 2 is a dependently typed language. And here's the exact same thing in Haskell. It just looks the same. It looks like dependent types. Agda uses an operator. We can do that as well. So we're faking Agda now. Here is how we can improve existing APIs using this functionality. For example, you're computing storage requirements for some data, let's say an array of 10 integers. And then previously you had to call the size of function with a dummy argument, undefined, and supply the type indentation. Now you don't have the dummy undefined. Same problem as we had with proxy, basically. Now we just say, how many bytes do I need to store 10 ints? 80, right? You just say, write size of, and then you supply the type. The new thing here, notice it wasn't possible before. We are using a type name in a term level context. So you're calling it size of. Now comes the term arguments. You would normally think, but hey, we're using bool. It is a type name. Previously, it would just tell you it's not in scope, but now it is. Here is another example, refactor, save, show, or maybe some other function. If you have database storage, you have a schema that you have to comply with, or you return JSON from a web service, and then you use classes to actually generate the serialized form of your data. Then it is prone to errors if you refactor your internal representation, because it's going to change the visible behavior of your program. You wanted to do a refactoring, but you ended up with a change in behavior. Now you can require the users of your function to visibly supply the type, which will determine the format of serialization. And here is a toy example. We can turn any type into a string using typable machinery. You just say show type, and you get a string. Again, new thing, previously wasn't possible. In the syntax of terms, we have the arrow. It is a function arrow, int to bool, but it uses the term level parser. This is the expression grammar, which has been extended. Now the arrow acts like an operator with the lowest possible precedence. Question, yes?
Can you go through this example? Yeah. So essentially A and T are the same thing, right?
Yes.
How do they interact with each other?
The question is, are those A and T the same thing? Excellent question. Yes. It's just that the A will be used in the rest of the type. The T will be used in the equation. If you had multiple equations, you could give it a different name in each equation, but it's going to stand for the same input. It's just a matter of scope.
So if you do another for all A without scope type variables, you could use A and T interchangeably?
So actually, visible for all with the arrow does not interact with scoped type variables. So it doesn't bring it to the scope. The A is not in scope in the body. But actually, we had an example here. You see with the @ sign. Now this is where we get the interaction. So if I used different names here, let's say S and T, then in the body, S and T would stand for the same input. They would unify with each other. They would be the same type variable under two different names.
And shadowing is otherwise available, is allowed here though. Like S, you wouldn't get a warning in this case.
Yeah, it's okay. It's okay. It's okay.
Yeah.
I'll do 2 more slides and then I'll do questions. So reifying type literals. This is an API that we all know. Probably if we use data kinds, we have type level symbols, type level natural numbers. We have symbol val, nat val for that using proxy. So the same thing applies as before. We just remove the proxy, and now we enjoy an actually good-looking API. We can even use a type family inside what looks like a term level argument, but actually we're using type families here. And then a conversion via intermediate rep. So imagine this read show. It does a read, then a show using some intermediate representation. If we used a normal invisible for all with a dot, then the type of that would be string to string, right? So it looks like a string to string. There is no way we could supply the type of the intermediate representation without type applications. That means an ambiguous type variable. Now we can say that part of the API is that the user, the caller, has to tell the function which intermediate representation to use. You can imagine in some algorithm, you could ask whether you want to use a hash map or an ordered map, something like that. And that was the first part of the talk, better APIs. I will now take questions about that part, and then we will move to the second part that actually is interesting, how it brings us closer to dependent types.
That was more a question in terms of implementation, whether there was any conflict with view patterns.
Yes, of course, that will be in the second part. If there is any conflicts with view patterns, yes, there are. Yes?
What was the choice for making the order of putting the constraints after the for all?
Yes. The question is, why is the constraint after the for all? Because before the for all, the type variable is not in scope. So the for all brings it into scope, and then you have the constraint after the variable is in scope, which is the same as with a normal for all. So if you have, here if we have this for all, then the constraints will come after the for all. Yes?
So the majority of your examples had like a binder on the left-hand side of a required type argument, and then on the right-hand side it could be used inside like a type annotation, like in this one. Yeah.
Yes. Yes.
So my question is, in this kind of usages, do you, or when exactly do you infer, like if Zavialov didn't have a type signature, would you infer that it's a visible type parameter because it has to be, because it's used in the time position on the right-hand?
Okay, the question is, I will try to repeat it and not butcher it because it's long, is how does inference work if the variable that we bind here on the left-hand side can occur in type positions? The answer is there is no inference for visible for all. GC uses a bidirectional type checker, which means it knows when you're checking a term against a type or when you're inferring a type for a term. Visible for all is only available in checking mode.
So it's never inferred?
It is never inferred. It is never inferred.
And in that case, would you get a scoping error? Or?
No, it would not be a scoping error. It would probably tell you that if you didn't have the for all, GC would think that T is a term level variable, and it would tell you that you cannot use a term level variable in a type context. And one more question, yes?
On the left-hand side, can you pattern match on it?
On the left-hand side, can I, what, excuse me? Pattern match. You can try. It will tell you that it does not unify with this column. Okay? But the syntax is there. Yes, you can write types or constructors on the left-hand side. If you later have an equality constraint, then it will unify. Okay. Now let's do some more theory after we had the practical examples, practical in quotes, of course. So if we look at the show function, I love its type because it has everything. It has a for all, it has a constraint, it has a term level argument. So if you look at the equation, we have 3 lambdas, meaning 3 inputs. First we have a type argument. Big lambda means it's a type argument. It will be erased during compilation. It will not survive to runtime. But it does look in the internal representation as an argument. And we say that show first takes the type of the thing that we'll be showing. Then for the constraint at the term level in the core representation, we have a dictionary that contains the method implementations. So for show, it will be show and showSprec, I think. So inside this dictionary, there is the actual code or a pointer to the code that converts the value to a list of characters. And then we have the actual value. So 3 inputs, a type argument, a term argument that is a dictionary, and a term argument that is visible. Correspondingly, 3 function-like types. For all is function-like. Constraints, the constraint arrow is function-like. And the function arrow is obviously function-like. And then when we are calling those a function, all of those 3 parameters will be supplied, always. Whether by you or by GC, they will be supplied. So when we call show normally, you can see I've colored int and dshowInt with a different background, slightly different background, meaning that you don't actually write those. This is what GC inserted for you. If you look into GC's code, you will find a type called HS wrapper for things that GC inserts for you. Those are those things represented by the HS wrapper, the extra arguments. So the user writes show 42, and those 2 just pop out from elaboration inserted by GHC. Or you have a choice of supplying the type argument visibly using the @ sign. What is the @ sign? We call it the visibility override, because by default, the for all bound type is invisible. You don't write it, but you use the @ sign and you tell GHC, no, I actually want to write it. You override the visibility of this argument. So here in this line, we have invisible, invisible, visible. On this line, visible, invisible, visible, right? But it's the same call. It is precisely the same code internally for GHC. And this allows us to classify the existing function-like types into what should be a cube, but I have only 2 dimensions here. Along 3 axes, visible, invisible, erased or retained, dependent or not dependent. The function arrow, it is visible because you visibly supply the function argument at use sites. You just tell the function what argument you supply, and that's how you call it. It is visible. It is not dependent because the value will not be mentioned. There is no name for it in the rest of the type for the function arrow. So the value of this argument will not be mentioned in B ever. There is just no syntax for that. And it is retained because the function argument will be passed at runtime. Now, in the invisible table, we have the erased dependent quantifier called for all. It is erased because it will not survive to runtime. All types are erased in Haskell. It is invisible because by default it is inferred. You can make it visible with the @ sign at use sites on a case-by-case basis, but by default it is invisible. And yes, it is dependent because this A here, it is in scope in T. It can be mentioned in T. And the constraint arrow is retained because the dictionary will be passed at runtime, or we will rely on specialization to remove a function argument, but it will still affect the generated code. And it is not dependent. Again, you cannot mention the dictionary in the rest of the type. Now, the holy grail, what we want to add to Haskell are pi types using the for each syntax here, which combines all the 3 properties. We want this. We want a retained, visible, dependent quantifier. Yes?
3 more minutes.
3 more minutes. Okay. So we want all the 3 properties. Now we're combining them like this. So the quantifier evolve along the dependent axis like this. We start with for all dot, which is only dependent. This is what we've added, required type arguments. It is dependent and visible. This is where the challenges lie in combining those 2 properties. And then finally, it will be dependent, visible, and retained. That's for the future. Now, the problems that we faced. Firstly, the for all keyword. It was not a keyword. We could name functions for all. Libraries did that, at least 10 of them. We had to deprecate those, and now we can write the for all because now the syntax is combined. Function type arrow versus view patterns. This arrow, and because GT uses the same syntax for expressions and patterns, is it the function arrow or the view pattern? GC got confused, and it also had different precedents with relation to type annotations. So we had to do some hacky things in the parser, which we will deprecate in the future. There is a warning. Users will be warned. Then we have punt constructors. So this code works. Now we introduce a data type which uses the same names. It suddenly doesn't work because those names override the names that we actually wanted. And we have to use this, whatever. It's a new thing for in explicit namespaces. We can tell GC, no, actually we do mean the type at use site. Yeah, here is an example of what you could do if you want to avoid it. We've introduced for listen tuples. There was also this punning issue. We introduced new names. Here are the new names. Thank you to Twig for implementing those. This is the no list tuple punts extension. They helped us. And then this is the capture problem. I don't have time now. Yeah, I don't. Just catch me in the hallways. So this is the scoping issues that we had to solve with implicit quantification. This is the ways to address the problem. This is the pipeline, how it works in GHC. We parse and rename as a term. Then we move to the typing pipeline and kind check and desugar as if it was a type. And this is the last slide, finally. This is how it's going to bring us closer to dependent types. We now have a good motivation to actually combine types and terms within GHC because they're almost the same syntax. Thank you.